Welcome to this explainer. Okay, today we are stepping right into a true crime forensic investigation, but definitely with a bit of a twist. Because instead of hunting down human suspects, we're actually going after a silent killer, one that's responsible for utterly destroying massive, heavy-duty machines. I mean, just imagine a colossal metal shaft inside an industrial plant, right? It's humming along perfectly for years, and then, completely out of nowhere, it violently snaps in half. Now, to an untrained eye, that just looks like a tragic, sudden accident, but as we're going to see today, these catastrophic breaks actually leave behind a very specific trail of clues. And if we know exactly how to read that evidence, we can catch this culprit before it strikes again.
Part 1. The Silent Machine Killer. Look, when a perfectly designed, structurally sound metal part just fractures, it is almost never a sudden accident. Engineers build these machines to handle absolutely incredible amounts of stress. So, what actually brings them down? Well, it's a stealthy, incredibly patient culprit that is actually responsible for a staggering 80% of all machine and equipment failures. No joke, 80%. If we can wrap our heads around this single, hidden phenomenon, we can drastically improve the safety of the machines we literally rely on every single day.
So what exactly is that 80%? It's something called fatigue failure. And here's the thing. This isn't about hitting a piece of metal with a giant hammer so hard that it instantly shatters. Not at all. It happens under completely everyday, seemingly safe conditions. You see, a machine is designed with a very specific maximum strength, and most of the time it's operating well below that safety limit. But if you apply repeated cyclical loading to it, whether that's tension, compression, or rotation, just over and over again, the metal simply gets exhausted. Think about it like bending a paper clip or a plastic chair back and forth. It obviously doesn't break on that very first bend, right? But it's that continuous, invisible repetition that ultimately kills the machine.
Part 2. Anatomy of a fracture. Now, to actually catch this killer, engineers basically have to act like forensic scientists.
When a machine fails, those broken metal pieces literally become an active crime scene. Because a fatigue fracture, it doesn't just happen all at once. It goes down in 3 very methodical steps. Step 1 is crack initiation. This usually kicks off at a totally microscopic level right on the surface of the metal, maybe at a tiny notch, a manufacturing defect, or just a scratch. And because it's practically invisible, I mean often just a few micrometers deep, you are never going to see it with the naked eye. Then we hit step 2, crack propagation. As the machine keeps doing its repetitive work, that tiny little crack slowly, agonizingly grows. It just pushes deeper and deeper into the metal. And finally, step 3, final fracture. By this point, the crack has grown so large that the remaining intact metal just can't handle the normal everyday load anymore. The metal simply gives up, and it shears off in one violent, sudden break.
Part 3. Naked eye investigation. When a failure like this actually happens, the very first thing investigators do is look for the macro-level clues.
The really crucial part here is knowing exactly what to look for right there at the scene. If you look at the broken ends of a shaft, you might spot what we call a cup and cone shape. That's a dead giveaway for a ductile fracture, meaning the metal stretched out a bit before it finally gave way. But the absolute biggest clue for fatigue failure is seeing 2 highly distinct zones on the exact same broken surface. Usually you'll see a really smooth, almost polished area. That smooth zone is where the crack was slowly growing, and the 2 sides of the crack were literally rubbing against each other over time. But right next to it, you'll see a very rough, jagged zone. That rough area, that is the final fracture zone. That's the part that tore apart instantly when the remaining metal just couldn't hold on any longer.
And hey, sometimes you get really lucky and spot something called beach marks. These are pretty wild. They look exactly like those concentric wave lines left on the sand when the tide goes out. These marks literally map out the progression of the crack for you. They happen when a machine goes through irregular load cycles, like maybe it runs really hard, then it stops, then it runs again. The crack actually pauses and restarts, leaving these visible rings behind. But there is a bit of a catch here. If a machine runs continuously under the exact same consistent pressure without ever stopping, you won't get any beach marks. So while they're an amazing clue when they show up, they aren't always there for the naked eye to find.
Part 4. The microscopic proof. Now, because our naked eyes can be pretty easily deceived, investigators have to dig a whole lot deeper using a scanning electron microscope. Under an electron microscope, the landscape of a break is just absolutely fascinating. If the break was a purely brittle failure, you'd see something called cleavage. It's this rigid, step-like surface that honestly looks like a jagged microscopic cliff face. But in the final, sudden fracture zone of our fatigue case, you'll usually see dimples.
These are tiny, hollowed-out little craters that show us ductile tearing, which basically means the metal stretched out at a microscopic level right before that final snap.
But hold on, dimples only tell us about that final sudden break. What about the slow, silent killing phase? Well, that's where we find our smoking gun. Striations. These are incredibly tiny, tightly packed, repetitive lines that you can only see under an electron microscope. And here's the crazy part. Every single one of those microscopic lines represents a single cycle of stress. One rotation of a motor, one push of a piston. If an investigator spots striations under the SEM, boom, case closed. It is the definitive, absolute fingerprint proving that cyclical fatigue was the killer.
Part 5. Catching cracks before catastrophe. Analyzing dead metal is great for solving mysteries after the fact, sure, but our real goal here is saving living machines.
Since we know fatigue almost always starts as a tiny microscopic crack right on the surface of a part, we actually have a way to fight back. We use what's called non-destructive testing, or NDT. Engineers use these really clever techniques, like penetrant testing, where they apply a special bright dye that literally seeps into completely invisible cracks, or magnetic particle testing, which uses magnetic fields to highlight surface flaws. By making these tests a regular habit, inspectors can expose those microscopic initiation points long before they ever get the chance to propagate into a full-blown disaster.
Let's look at how this plays out in a high-stakes, real-world scenario. Let's say you manage a big industrial facility, and you've got 3 identical pumps. Suddenly, pump A fails catastrophically at 30,000 operating hours. You run the forensics, you find the striations, and you confirm, yep, it was fatigue failure. Okay, so now you look at your other equipment. Pump B is currently running fine and has only logged 20,000 hours. But pump C, it's also running seemingly fine, but it has logged 50,000 hours.
So, what do? Well, you definitely don't just wait around to find out. You take urgent action. Because pump C is sitting at 50,000 hours, meaning it has endured significantly more cyclical loading than the 30,000 hours it took to completely destroy pump A. It is essentially a ticking time bomb. It must be halted immediately. I mean, even though it looks totally fine on the outside, there's an incredibly high probability that a microscopic fatigue crack is actively propagating inside it right at this very second. So you shut it down, you run the non-destructive testing, and you find that crack before the machine violently tears itself apart.
Fatigue failure is truly a master of disguise. It doesn't scream, it whispers, building up damage cycle by cycle, day by day, until the very last possible moment. But by treating machine failure as a true forensic science, engineers can read the beach marks, spot the striations, and actually outsmart this silent killer using proactive testing, which leaves us with a final thought to ponder as we wrap up this explainer. Look around at the cars, the elevators, and the infrastructure you use every single day. What hidden microscopic stresses are accumulating in those machines, just waiting to reach their breaking point? Definitely keep that in mind next time you hear a motor humming along. Thanks so much for joining me on this deep dive.